It is my great pleasure to welcome Professor Sharad Sane for this lecture in the Mangala Narlikar Memorial Lecture Series. This is the 6th lecture in this series. Professor Sharad Sane was Professor of Mathematics at Mumbai University. Then he was also visiting professor at IIT Bombay, and then in Institute of in CMI, Chennai Mathematical Institute, and now he is residing in Pune. He is also adjunct professor at the Bhaskaracharya Pratishthana. He will be today talking on the topic coloring, least coloring and Latin squares. So I request Professor Sane to start the talk.
So I thank Bhaskaracharya Pratishthana for inviting me to give this talk. In fact, it's a pleasure to give this talk in the memorial series for Professor Mangala Narlikar, who was a good teacher, and incidentally I got to know almost more than 20 years ago. There is an anecdote that I'll refer to during the talk, that Mangala Narlikar thought that she has proved the 4-color theorem, and Professor Katre referred her to me when I was in Mumbai, and there was a small gap in the proof, I mean, as it happens, but I'll refer to that a little later during the talk. So it's probably in the fitness of things that that one talks about the coloring problem. Okay, so the basic setup, all the graphs, n vertex graphs, E edges, generally the vertex set is denoted by V and the edge set by E. This is a fairly standard terminology notation. And this is what the entire thing is going to be. Coloring graphs, chromatic number, coloring planar graphs, least coloring the we'll see why it is harder and how it is connected with the coloring question, then directed graphs, and okay, this is a standard definition of proper coloring. What you want is, if two vertices are adjacent, then they should receive different colors. That is all there to it. So all the colorings, whenever I use the term coloring, it means proper coloring. The smallest number for which you can color the graph in k colors, and smallest k, that is called the chromatic number. So graph is said to be k colored, and take the smallest k for which this can. For example, the only graph that can be one colored, for example, is the one that has no edges at all. It's quite trivially. There's nothing to check there. And the one that has chromatic number 2, in fact, can actually be characterized. This has to have edges, and it's what is called a bipartite graph. It is a bipartite graph. So essentially a graph is bipartite if and only if it is bipartite. Exactly when it is bipartite, those parts form a partition of the vertex set with no edge inside a part. And that is why you need 2 colors, and 2 colors are sufficient. Yeah, that's the chromatic number. This is the minimum. So we can now assume that f is a surjective function from the vertex set to the set of first k integers, and these are called the f inverse of I. This is the, so all those vertices that receive color I, they form the non-empty set Ai. This is an independent set. There should be no edges inside Ai, and that tells you something about the chromatic number. So if I know the largest size, each color class, this is what we mean by f inverse I is a color class, it is the ith color class. Each color class is an independent set and if I have the bound on the size of independent set in a graph, and this is generally denoted by alpha g, then that gets me the lower bound on chromatic number. This turns out to be reasonable. For example, something like bipartite graphs, this is quite good. In fact, essentially equality. I mean, you need to take integer on both sides. So,
Is it n or k?
say that again. Sorry?
What is n?
N is the number of vertices,
One number of it.
total number of vertices. So, it's a, yeah, I mean, so the ambient set for on which I am acting, the vertex number of vertices is n. Other parameter is the clique in a graph. This is the largest complete graph, the largest size of clique is the clique number. If you have a clique, it means every two vertices in a clique are adjacent to each other. Therefore, the chromatic number has to be at least as large as the clique number. So, there are two very crude bounds that one has here, the one that is given in 1 and the one that is given there. Unfortunately, essentially it is only very elementary kinds of graphs for which equality is going to hold there in 1 or 2, and per se not very interesting. This is the idea of greedy algorithm. What you do is you sequence the vertex set in the order, so the first vertex, second vertex, etc. F of Vi is the smallest color which has not been used on any one of the neighbors of f of Vj, that is already. So, greedy works, greedy is a generic algorithm. So, it is a generic algorithm where you do get an upper bound on the chromatic number. Those many colors will suffice, they will certainly suffice. What is the catch? Why did I call it generic? It's generic because everything seems to depend on that order. The order in which I sequence those vertices, how do I know which one to take first and how do I know which one to take second, etc. Typically, for example, as I said, elementary examples, greedy works for on the complete graph Kn. This is clear. No matter how you sequence, it's going to be, you will need as many as n colors, and that's clear. That's the chromatic number also. Greedy can fail. See, look at this. This is a path. I am giving that vertex color 1. After that is sequenced that vertex which gets color 1, because these are W and X are not adjacent. Therefore, the idea of greedy is it's stingy. It tries to use as less number of colors as possible. It tries to. Then Y has to get color 2 because it's already adjacent. Now, Z is sandwiched between color 2 and color 1. Therefore, Z has to be given color 3. On the other hand, for this graph, this is a path. The chromatic number is 2. It's clear. All paths have chromatic number 2. All paths are bipartite and therefore their chromatic number is 2. So, right here something went wrong with the sequencing. It's just I should have taken this vertex first, then that vertex, then that vertex, and that vertex. And a lot of this is motivated by applications in computer science as always, and therefore the point is this is programmed. You would not know this sequencing beforehand. There are classes of graphs for which it is possible to know. So, those are good classes of graphs for which sequencing can be arranged, but those are not far too many. That is the whole point. I will get to this little later. Now, that example can be blown up. I mean, I have just I've basically taken the same example. You see, those are 3 copies of the same thing. Now, that vertex has to be, an extra color has to be pulled out for that vertex, which is number 4. And then you can go on building on this. You can basically go on, this is a tree. This is an example. This is a tree, those are paths, and that is, so this tree, which is bipartite, actually has chromatic number equal to 2, but the sequencing that we have gotten here, it requires as many as 4 colors. Therefore, it is a bad sequencing, but one would not know beforehand. So, that is the first theorem. A tree along with a vertex ordering that requires, that will require as many as k colors, and you can let k go to infinity. Okay. So, it can really be very bad, whereas the chromatic number is equal to 2, because all trees are bipartite graphs, there being no cycles. And this is exactly where the theoretical computer science takes up. I mean, they say, all right, it's a bad algorithm. I mean, greedy is a, how bad can it go? Randomly chosen. Suppose I choose my sequence randomly, how many times will it fail? I mean, is it, I mean, one picked up the worst example, but one doesn't have to pick up the, so there are proofs of this kind that probabilistically one can get as many as twice the chromatic number of the graph, which is not very bad. Which is not very bad. If the chromatic number is equal to 100, then it makes a mistake, maybe it may give an answer which is less than or equal to 200, which is considered okay for many situations. Largest degree, in fact, this is number 3 is a consequence of greedy. It's just a consequence of, if with any sequencing, if one applies the greedy algorithm, this is what one will get. The largest degree, 1 plus the largest degree. Equality holds here for complete graphs. Actually, you have equality here, and there is a theorem of Brooks. So, it says that except for complete graphs and the graphs that contain odd cycles, even cycles have chromatic number 2 because they are bipartite. Odd cycles have chromatic number 3. Except for odd cycles and the complete graph, this can be improved to delta G on the right side. So, the right side can be slightly improved. This is what is called the Brooks theorem. In fact, inductive proof, it's illustrative. Most of the textbooks do give proofs of proof of Brooks theorem. It's quite roundabout. I mean, if one has to make several one by one assumptions, connectedness, one connected, two connected, etc., etc. But it's a nice proof. Okay, now I get to the point of coloring planar graphs. In fact, the coloring problem historically began when people started coloring planar graphs. G is a planar graph if it can be drawn on the plane without edges crossing each other, except at the vertices. Interesting examples of planar graphs: the tetrahedral graph, complete graph on 4 vertices. The cube graph, this is bipartite. Cube graph is bipartite and has chromatic number 2. The octahedral graph has chromatic number 3, dodecahedral, icosahedral. This is the Euler equation that governs relationship between number of vertices, number of edges, and number of faces for a connected planar graph. Many proofs are available, but this is something that has to be on back of mind. Euler formula typically proves, for example, that the complete graph on 5 vertices, this what is called the utility graph, 3 vertices on one side and 3 on the other side, and you draw a complete bipartite graph. They are both non-planar. Peterson graph is also not planar. This Oedipe theorem of Kuratowski says that all non-planar graphs, in some sense, they contain copies of K5 or K33. Proof of the 4-color theorem that was obtained about 50 years ago now, it was shown by Kemp, I mean this major work 100 years ago, now 100 years ago, that every planar graph can be 5-colored. Argument used in Kemp's theorem is, this is now called the Kemp chain argument. What Kemp did believe himself was that he proved 4-color theorem, which he did not. There was a gap in his proof. And now getting back to the anecdote that I talked about, Mrs. Narlikar more or less had made an error which was similar to the one made by Kemp. It's just that Kemp's proof, Kemp's claim that he proved that every planar graph is 4-colorable, it remained without challenge for 20 years. Almost for 20 years, people believed that Kemp has given a proof and it's correct. This was around 1910 or 1910 to 1920. And this argument is the Kemp chain argument. Now what I am going to do is introduce a different coloring parameter. It is quite different. Initially it looks quite innocuous, looks very similar. It is similar to the chromatic number, but then you will see that it is actually quite different. This is called list coloring. What one is going to do now is, it's a sequence of sets. Each set has order k, and at the vertex I, you can only use the colors that are there in AI. You can use only those colors are allowed. And if you can properly color it, then it's called list coloring. F of Vi should come from AI, and F is a proper coloring. In that case, you say that it's list k colorable, list k chromatic. The smallest k for which this can be done is to be called list chromatic number. If this is true for all choices of A, then it's k choosable or k list colorable, smallest k for. So I am going to use the subscript L for list coloring. List coloring is a proper coloring, and therefore chromatic number is less than or equal to the list coloring number. So if I can work hard and succeed in proving some list coloring number, then it gives natural an upper bound on the chromatic number. That is why this it also exists, because this exists is very clear. I mean, there is hardly anything to check there. You just for every set you create a set of order n. For every vertex you put a set of order n. Then it is clear that no matter which vertex I am at, I always have one color at my disposal. That is clear, because the total number of vertices is only n. So I mean, if I replace that kn by g, then it is just less than or equal to n. That is what it will mean. Similarity between chromatic number and least chromatic number is in this theorem. Okay, this numbering is wrong. No, that theorem is 1.2, and this also is proved essentially using greedy algorithm. This can be done. You sequence so take k to be equal to the right side, 1 plus delta g. On every vertex you have a set of order k sitting on head of every vertex. No matter how you sequence, those many colors will be sufficient. All right, this is slightly a graph theoretic detour. So This is a standard definition: connected if there is a path between every two vertices, two connected if there are disjoint paths between every two vertices. Essentially, two connected graphs are modeled after cycles. They are just modeled after, it's just that not every two connected graph is a cycle. I mean, that's too elementary statement. So, every two connected graph is gotten using bundles of cycles, I mean, twisted one into the other. This is generally referred to as ear decomposition. The standard term here is what is called the ear blowing up and ear decomposition. A triangulation of planar graph is obtained by adding edges to G without disturbing planarity. This is the main point. Set of vertices is fixed. I am going to fix the set of vertices, but I am free to add edges by adding. If I start with a planar graph and if I add a non-existent edge, an extra edge without crossing, then I am creating one extra region, one extra face, and I also am adding one extra edge. Therefore, Euler equation still holds, and one can go on doing this. So, this is my graph is triangulated if every face is a triangle. It has a near triangulation if all the vertices are either on a cycle or all of them are stuffed inside a cycle, all of them inside a cycle. Both these situations can be obtained. I mean, the given graph need not be triangulated, but I can always triangulate any planar graph. Any planar graph can be triangulated by adding extra edges so that every face becomes a triangle. Every face, including the one that is the infinite face, the outside face. Yeah, that is for connected. Yeah, if I break here at this vertex, so what will happen is, I mean, at this vertex, those will split into two parts, etc. So, that is called a cut vertex generally. Planar graph, if it is maximal, then it is two connected. If my graph is disconnected planar, then I can always add an edge from one component to other component, that is quite clear. Therefore, WLOG I can assume that for this purpose that everything that I do is connected. Okay. If G is maximal, then it is even two connected. Maximal planar, then it is triangulated. And a given graph has an embedding in the sense of adding extra edges, that is what it means. Okay, this is the major theorem. Where we are headed to is, I want to give a sketch of the proof that every planar graph is list phi colorable. Okay. This is quite an achievement. Therefore, it will automatically also prove that every planar graph has chromatic number less than or equal to 5, because chromatic number is bounded by list chromatic number. So, if I prove that a planar graph has list chromatic number at most 5, so this is a proof by graph theorist Thomason, and it is quite interesting proof. It is induction based. It is proved by making induction. Let me go over this. So, this is near triangulated with the outer K cycle. Assume that at every vertex a certain list is given. So, this is like list coloring, it is just that it is more special, it is more general than the list coloring. At every vertex you have some set of numbers that is put on every vertex, and these sets need not have same cardinality even. So, the list at V has at least 3 colors. For every V which is not on the outer cycle, there are at least 5 colors available. At x1 you already fixed the color 1, at x2 you fix the color 2. Then what this is saying is this can be extended to a proper coloring such that g of x1 is 1 and g of x2 is 2, and at every, this is not written there, so it should be written there, at every other vertex the color that that vertex get is as per stipulation. The idea of the proof is making induction. Assume that this is true for n minus 1 vertices, and you have n vertices now. That is a typical proof in the topological graph theoretic sense. The outer cycle, the big cycle, there are two cases. Either it has a chord or it does not have a chord. If it does not have a chord, what it means is that the outer cycle, inside of the outer cycle is completely triangulated. I mean, what you see inside that huge cycle is triangulated. Every region is a triangle. Now the chord divides that cycle into two parts, x1 and x2 both, x1 and x2, I did not say that, okay, the x1 x2 is an edge, so that they are on the same side. And that along with t is, so one part you denote by C1, the other side you denote by C2. So the corresponding graphs by G1 and G2, they meet only at YZ. So these are smaller graphs, therefore by some induction, these are near triangulated, so the only edge, so using induction we can extend the coloring to all vertices of G1, so that both Y and Z receive a coloring. Now using this coloring for Y and Z, we can extend it to all the vertices of G2, so as to color. So this is a straight induction. More difficult case is B, that's a more, it's possible that there are no chords at all. So what has happened here is x1 and x2 are adjacent, they are on the outer cycle, and that outer cycle is, it goes from x1, x2, x3, etc. all the way to xk. The neighbors of xk are xk minus 1 and x1 and the other things. Interior of C, it's every face a triangle, therefore you will get these triangles. This is little involved, this proof is involved. So what you now do is tentatively at xk, where there are 3 colors available, L of xk is given to have 3 colors, pull out 2 colors which you want to reserve and which you want to use later on. Then all the things they follow except the vertex xk, everything else can be colored, because I will have as many as n minus 1 vertices. There will be a cycle inside which all the vertices fall except the vertex xk. So all the n minus 1 vertices will be inside that cycle. Then I can use induction. One of the reserved colors J and L is chosen for xk, that depends on what color is given to the neighbor, etc. x1 has color 1 and the colors J and L have been removed from the neighbors. This depends on the color of xk minus 1, which could be J or L, but not both of them. We could suitably choose a color for xk. Okay. This is a very nice argument. It's really quite elementary, but very neat and nice argument. Why is it not moving? Yeah, so the consequence of this argument is that it's a planar graph. Adding edges, we can assume that G is triangulated. So inside the boundary, now extend this can be extended using that main result that we proved, induction based result. So that's a result of Thomason, that the least coloring number for every planar graph is at most 5. In some sense, the proof of Thomason's theorem parallels that of Kemp argument. It is similar to the Kemp argument. It is not same, but it is similar. Kemp chain argument also makes use of induction. So, this is in some sense encouraging. So, one may be tempted to believe that if this can be pushed to least coloring number at most 4, then it will prove the 4 color theorem. It will actually prove the 4 color theorem. It turns out that the least coloring is a much harder combinatorial problem than the chromatic number. Let me dwell on this for a few minutes. Chromatic number, finding chromatic number of a graph is at the heart of graph theory. I mean, it is at the heart of graph theory essentially, except for one colorability and two colorability, no characterizing results are known. It is not known how exactly a 3 colorable graph should look like. It is not known. Just as you know what is a 2 colorable graph, it is a bipartite graph. You have no idea of how these can be quite weird, they can be very complicated. And a lot of interest also comes from the determining those two parameters, the clique number and the independence number. If the independence number can be reasonably determined, then the chromatic, it will shed some light on the chromatic number. Now the hierarchy level is chromatic number is a harder problem, independence number is connected, but it's if you can solve independence number, then so it's even a harder problem or is connected. In case of chromatic number, you need disjoint sets, each one of which is independent. So it's asking for more, asking for lot more. There is no good algorithm, essentially good in the sense polynomial time algorithm, known for finding independence number of a graph. It is not known. It's a very hot question in the theoretical computer science domain. Every bipartite graph has chromatic number 2. Okay, so it's a good enough. So what I have done is there are 6 vertices here. I want to check whether it is its least chromatic number is 2. So on every vertex there is a set of order 2 that is put on every vertex. There are 2 vertices there and 4 vertices there. This is a complete bipartite graph, 2 on one side and 4 on the other side. Without loss of generality, I give color 1 here and color 3 here. Now there is a problem on how I cannot really choose a color for this vertex at all. Now this is the same thing if I give color 1 here and 4 here, because there is a vertex present there. Okay. What that means is this graph is not least 2 colorable. Its least chromatic number is bigger than 2, it is larger than 2. I mean this, it's a kind of counter, I mean on every vertex you have given set of order 2, and this cannot be colored by choosing colors that come from that set. In fact there are ways in which you can blow that example out. Least chromatic number goes going to infinity for some bipart. Here it is, What you do now is take an integer k and m, a large integer is a binomial coefficient. On both sides I have m vertices on both sides. It's a complete graph, complete bipartite graph. I want to say that the least chromatic number for this is bigger than k, it cannot be k. It's the idea of the proof. So that's a bipartition. Distinct k list with every vertex. After all, I mean, one is short of words here, because complete bipartite graph gets defined as soon as It's a more set theoretic abstract concept. What I am going to do is on every set I am going to put a set of subset of order k of a set of order 2k minus 1. I can do that. I mean, this will obtain a distinct because M is 2k minus 1 choose k. First of all, it cannot be list k minus 1 colorable, because if there is a k minus 1 subset, then there will be a complement of that does not pick up any one of those colors, and therefore k minus 1 do not suffice. Even k do not suffice, because if it is k, then on one pan, on one side, those k colors would be used, all of them. Then there is a vertex on the other side that has exactly those k colors, and therefore it cannot be colored. Yeah, this is also its notation q is slightly misleading. Q is not a prime power, q is any integer. Q is actually just any positive integer. Yeah, it's just need modulo z modulo q. So one could ask a pertinent question: chromatic number, least chromatic number are equal at least for planar graphs. This turns out not to be the case. Smallest example, least number of vertices. Initially, some 50 years ago, the smallest example had more than 100 vertices. At present, the one with smallest number of vertices, n is equal to 63 vertices, and this is example by Fields medalist Mirza Khani. It is a complicated graph. I mean, the full page, it's actually drawn on a full page. I'll get to this towards the end of the talk when I give references. Okay, I think I'll just take a few minutes break. Yeah, because in fact, remaining part of the talk is going to be combinatorial completely. So from topological things, we are going to shift to combinatorials completely.
Function which is number of least colorings of a graph.
Sorry?
Number of ways a graph can be least colored.
No, that will be a more difficult question.
Something like a polynomial. Is it a polynomial function like chromatic polynomial?
Okay, in that sense. No, I don't know. I'm not really aware of that. Okay, I see what you're saying. Yeah, I mean, give more colors. Yeah. Yeah. Analog of chromatic polynomial is. Yeah. I think initially when they started, they didn't think that least chromatic number will be much harder problem than the chromatic number, but it so turns out that it is actually a much harder problem. Let me give an idea of what finally I am going to do in this second part of this lecture. This is what is called the Dinitz conjecture. You take a square grid. So, take m by m grid, m square vertices. Every two vertices are adjacent if they are in the same row or in the same column. It's a pretty simple definition of that graph. This graph has a chromatic number equal to m. It is equal to m, and this is basically is equivalent. I mean, that this graph has chromatic number equal to m is equivalent to saying that Latin squares exist. Latin square of order m exists. So, it is exactly restatement of that. So, what we want to do is obtain a least coloring for this graph. So, its chromatic number is already equal to m, as I told you, it is equal to m. But from that it is not obvious that the least coloring number is also equal to m, and that is what is called the Dinitz conjecture, and this was proved only about 20-30 years ago. Okay, that is the idea of directed graphs. My directed graphs are simple. So, it is simple directed graphs. So, take a simple graph and direct the edges, it becomes a directed graph. No loops, no multiple edges. From x to y, either you have direction from x to y or y to x, but not both of them. That is the definition of kernel of a digraph. So, kernel is an independent set. That means between every two vertices there is no edge from one vertex in the kernel to other vertex in the kernel. And if you are outside of K, then there is a y in the, if x is outside K, then there is a y in the kernel such that you can go from x to y. So, from every vertex which is outside, you can jump into the kernel. Okay. Notion of kernel is ancient, almost 1930-40s. This is a very important definition for mathematical game theory. It is a very, lots of idea of kernel is necessary for all these things like NIM games, various kinds of things. It is exactly this definition that is required. So, and many mathematical games can be theoretically, in principle, can be won provided you know the kernel. So, this just depends on difficulty in finding the kernel of the directed graph. Yeah, so this is the directed graph. B, C, F, my claim is B, C and F are in the kernel. So, from outside, from A you have an edge to F, so you are okay. From E you have an edge to C, you are okay. And from D you have an edge to B. Therefore, this is a kernel, B, C, F is a kernel. Directed graph may have several kernels. It is possible that it has, it is just that we want to have one kernel. Just to say that the notion of kernel may not make sense, as an example, take an odd cycle, take an odd directed cycle, it does not have a kernel. Leave it to you to check this. Take a cycle of odd length and direct all the edges clockwise, it cannot have a kernel. This is the main theorem, that at each vertex x of the directed graph, a color set is given. So, this is more general than the least coloring. These sets need not have the same cardinality. Every induced subgraph of G has a kernel, and for all x, the colors given at that vertex is 1 plus the out degree at x. Then there is a coloring f of G such that at every vertex f x belongs to C of x and F is a proper coloring. This is a powerful theorem. Fortunately, it has a easy proof, induction. Induction does work here. Let's see how. This result is true when n is equal to 1. Assume that the result holds for all graphs with strictly less than n vertices. Alpha is some color in some list. Look at all those vertices that receive the color, whose list contains alpha. Pull all of them out. Call that H the induced subgraph. H is the induced subgraph on all those vertices. By assumption, H has a kernel because we assumed that every induced subgraph has a kernel. This is an assumption. Using the definition of K, so that kernel is K, we can color all the vertices in K by color alpha because K is an independent set. Kernel is an independent set. G prime is the induced subgraph of G whose vertices, these are all the vertices that are not in K. These will be, some of those will be in H and some not in H. Delete the color alpha from every list. G prime in G prime. This has less number of vertices. So, the proof will be complete if we show that G prime also satisfies 2. What is 2? Yeah. So, it is this inequality here. Vertices of G prime that are in H, at least one out degree is killed because there is an H towards the kernel by definition. Therefore, out degree is reduced by 1 and therefore, that same inequality still holds. For those that are outside, the out degree remains same, but nothing is changed. Those that are not in H, the color list remains the same and so the same inequality holds. Therefore, you are quite all right. So, giving color alpha to all the vertices in the kernel and the proper coloring to all the things in G prime gets you coloring for G. Throw in one more definition. So, that is a standard notation for bipartite graph. X is one part, Y for the other part, delta for the set of edges between X and Y. Matching is a set of edges, no two sharing a common vertex. The maximum matching is one whose size is the largest. Numerically largest, that is called the maximum matching. I am going to have to skip some technicalities here, so you can read them, I will give references then. Yeah, the bipartite graph is a model for many real life situations. It is a very important model for many real life situations. On one part you could have job applicants and the other part you could have companies that provide jobs. Not every person is suitable for every job and therefore, and not every person would like to do all the jobs, he also may have his preferences, etc. This is a plain question of finding a maximum matching. You want to, why does one find a maximum matching? You want to pair up as many things as possible, as large number of things as possible. This is a very elementary quantitative parameter. One can do better than this. One can put weights on edges. This can be done. One can actually put weights on edges, and by doing that one talks of what is called weighted bipartite graph matching. This is also required. This is also required in many situations. It is a large number of applications. All these are basically offshoots of the so called network flow theorem are all parts of network flow theorem, but weighted bipartite graph is an important concept. Besides this, one can even have, for example, if this in the situation of boys and girls, where the pointer is not, oh okay. It is possible that every boy knows a certain number of girls and he has a preference list on the, so there is a ranking that is there, and then in some sense you want to match, you want to make as many pairs as possible. So the happiness here will have to be qualitatively defined and will have to be put in terms of quantity. I will get to this a little later. So it is a very vast area, preference list and how to rank these things, etc. So it is a ranked bipartite graph. So you can treat this small ABCD as set of boys, capital ABCD as set of girls, and every boy has a preference list. This is what is given here. A prefers capital A to capital C and B has a preference in that order, C has a preference, D only likes A and capital A, it is that order. A possible largest matching here is this. This is a maximal matching, it is also a maximum matching. You call a pair of boy and girl pair unstable if in the preference list of small x, x prime is ahead of x. And in the preference list of x, x prime is ahead of. What it plainly means is, if there is a pair that is unmatched, a boy-girl pair that is unmatched, and boy prefers the unmatched girl to the girl with whom he is paired, and the girl also prefers the boy to whom she is not matched to the one that she is matched with. In that case, that pair is unstable. That pair is unstable. Lack of instability is stability. That's exactly the definition of stability here. So stable matching means something that does not have unstable pairs at all. It's not quite clear whether stable matching will exist. And purely as a mathematical query initially that it came, these two people, Gale and Shapley. Yeah, okay, that matching that I showed you, where you get as many as 4 pairs, is not stable. The pair CA is unstable. This matching is a stable matching. Stable matching is a maximal matching. That is a theorem of Gale and Shapley, proved around 1990, which says that stable matchings exist. Stable matchings always exist for any ranked bipartite graphs. In fact, this theorem is proved using an algorithm that is now called the deferred acceptance algorithm. Initially, when Gale and Shapley did this, it came more as a mathematical query, something interesting mathematically, etc. Around 2005 to 10, another person joined them. Probably Gale was no more by then. Shapley and Roth. They showed social science applications of Gale-Shapley algorithm, very large number. I mean, and for that discovery, the Shapley and Roth both received the Nobel Prize of Economics. This is around after 2010, sometime probably 2012 or 14. So it is a theorem that is used highly in social sciences. I mean, ultimately in all these things, the what is meant by being happy, happier, etc. These all have to be defined properly and then mathematically translated. And so the game lies there. So the algorithm is pretty simple. Boy looks at his preference list, and whichever girl is at the top of his list, he goes and proposes to her. What may happen is the girl may, initially she just asks him to wait, and if she receives a better proposal, then she rejects the boy, he goes down his list, he goes to number 2 on his list, and this continues. Okay? So this is the idea of deferred acceptance algorithm. Yeah, so one feature of this algorithm is that a girl always finds a match as soon as she is proposed.
What happens to the weight here?
No, there is no weight here. There is no weight here. No, it's
It says that the girl
no.
asks the guy to wait.
Oh, waiting. Yeah, the waiting. Deferred. That's exactly what is meant by deferred. Deferred acceptance. Yeah, waiting is equal to deferred acceptance.
So there will be multiple rounds.
There will be multiple rounds. That's quite correct. I mean, this also estimated. There could be as many as, if there are n boys and n girls, there could be as many as n square rounds. Okay? One can create situations. It's also mathematically studied now. I mean, quite well studied. There's a metroid that one can get on this, so on and so forth. Is that clear? Yeah, there could be several rounds. What is nice about this is, no matter how you approach this whole thing, the final outcome will be same. It's not per se very clear, but it will be same. So what is produced by DA algorithm is unique. The pairing is unique. Okay. Okay, that's the definition of Latin square. I am getting to the end of my talk. Please ask any questions if you have. Latin square is an n by n array of numbers. For every row is a permutation, every of the numbers 1 through n, and every column is a permutation. Latin squares exist. For all orders, Latin squares exist. Easiest way of constructing this is to just write numbers 1 through n and then cyclically shift them. So that's also, you get a permutation. So if you just shift them cyclically, this in fact, this is what is called cyclic Latin square. It is called cyclic Latin square. In particular, group multiplication table of any group is a Latin square. That's clear. The cancellation is all that you require here. Okay. So you don't need a group. In fact, you need algebraically even much weaker structure will also do. That's the definition of line graph of a graph. In fact, I am going to look at only the complete bipartite graph. Take 5 more minutes, is that okay, Katre sir? Yeah. So we are going to take a complete bipartite graph. You can treat it as rows of a chessboard and columns of a chessboard. So there are n rows of a chessboard and n columns of a chessboard. So what you see is every cell then actually corresponds to edge there. So you now have a graph on the edges. That is what is called the line graph. 2 vertices are adjacent exactly when they are in the same row or same column. That's the last part there, n by n grid, for each vertex ij, you are given a list of size n. That list is arbitrary. It is possible to color the grid graph properly, choosing a color for every vertex from the list associated with that vertex. Let me say something why this problem is considerably more difficult than determining the chromatic number of this graph. Chromatic number of a graph gets determined as soon as I find disjoint independent sets whose union is equal to the vertex set, whose union is equal to the total vertex set. That is exactly it, and do it in a minimum manner, etc. In this situation, if I have a Latin square actually, and Latin square can be superposed on that grid, then wherever the number 1 appears, they cannot be in the same row or same column. That is the definition of Latin square. Therefore, that forms the set of cells of the Latin square on which 1 is written, that forms an independent set, or for that matter on which any fixed j is written, that forms an independent set. So, we have as many as n independent sets, each of size n, therefore, the chromatic number is equal to n. It is clear. I mean, chromatic number for the grid graph is equal to n is equivalent to saying that Latin square exists. Latin square of order n exists. This cannot really be done here. I mean, it is this cannot be done here for the Dinitz conjecture, because now these lists are arbitrary. These lists are, all we know is this, each list has size n, but these lists, they are not the list 1, 2, 3 up to n. So, you cannot really take a single Latin square and work through that. Okay, so this is the idea here. I will skip this proof. In fact, this does depend on the roughly it works like this. What you need to do is I did allude to directed graph. So, what you need to do is the chessboard graph. I mean, just take the chessboard as a model. So, you have as many as n square vertices there with 2 vertices adjacent to each other if they are in the same row or same column. You need to put directions here on. So, horizontally you need to put directions and vertically also you need to put directions. This job is done by using Latin square. This is done by using Latin square. So, that is exactly, and then the kernel for this graph, you need to prove that every subgraph has a kernel. A subgraph here will mean a set of vertices which is set of cells on that chessboard. It is just set of some cells out of those n square cells. Some cells are picked up. That graph, you need to prove that it has a kernel. This requires use of the fact that stable matching exists. So, this is where the stable matching idea is taken from there in a very crucial manner, and nobody believed that proof of the Dinitz conjecture will work that way, okay, but it does. And what he is doing is horizontally the ordering is a natural ordering. So, if the number is, if one number is less than the other, then you put the direction from the smaller number to the larger number. On columns, you put the direction exactly opposite of that. By doing this, all the assumptions that we need, out degree will be exactly equal to n. What that number is irrelevant now, because there are as many as, if j is my number, there are as many as n minus j numbers that are larger than j, and j minus 1 numbers that are smaller than j, okay, making a total of n minus 1. Therefore, the out degree for every vertex will be equal to n. The fact that this induced subgraph has a kernel is that is based on the Gale-Shapley algorithm, and that finally clinches the issue. So, those who really want to work further, I did try to an extent, but did not quite work. It is possible to put 2 Latin squares, so on and so forth. It is possible to make a graph and then make least coloring conjectures on these graphs, but there is no natural ordering here. At least I could not find one. Okay. Okay, so yeah, those are the references. That's a paper of, yeah, in fact, number 4, early paper of Mirza Khani is what it is saying on Math Archives. This is in 17, and that paper is not published in a very well-known journal. Okay, 2 and 3 I treat as essentially standard books on anyone who wants to do anything higher level of graph theory. So, okay, so thank you.